what we as society do to the landscape and what nature does to the landscape itself over various different time scales and on various different spatial scales. This is Lisa Penfield. Lisa is a student from Tufts University who is visiting Clarkson over the summer and working as a research assistant in my lab. And I was asked by Tim and the board of directors here at the fort to come talk to you today a little bit about the site that we're standing on and how this site may have come to be. So the time frame that I'm going to talk about goes all the way back to about 25,000 years ago, which is where we're going to start. Now, 25,000 years ago was the very height of the extent of the Laurentide ice sheet, the big glaciers that came over the North American continent. And if we were standing at this spot back in 25,000 years ago, there would be about 2 kilometers of ice, about 1.5 miles of ice on top of us. And if you wanted to get to the edge of the ice, you would have to walk due south to just over the Pennsylvania border to get to an area where there wasn't any ice. Now, those glaciers that came across the landscape and moved to the south did great change and great work on the landscape. They created things like our Finger Lakes, they created the Great Lakes, they sculpted the Adirondacks and the Catskills and the Appalachian Mountains into the rugged forms that you see today. So the mountains, the Appalachian Mountain Range north of Pennsylvania has a very rugged look to it, much more like what you would see in the Alps, although much lower. When you get south into Pennsylvania and south, it turns into basically just a nice wrinkled, rumpled carpet. And that rumpled carpet is some of the high peaks down in the Lake Placid region are all evidence of this activity of glaciers that have moved through the landscape. As those glaciers moved from Canada down across the United States, they scraped like a bulldozer the Champlain Sea, the retreat of the Champlain Sea, the river systems that flow north, and then what society has done to that landscape. So all of those are chapters in our book. And this piece of equipment is a ground-penetrating radar. The ground-penetrating radar can look through the layers in the subsurface to help us understand what has gone on in an individual place. Because each one of those events tells a story and lays down sediments in a certain way that is characteristic of those events. And the ground-penetrating radar will actually show us some of those layers, and we can then interpret the wiggles on the screen to be able to unravel the process that happened to be able to create those layers of sediment. Now, I am sure there are probably some people sitting out here who've had experience with ground-penetrating radar, but in a different format. Has anybody ever been to the hospital and had an ultrasound done?
Yep.
Same technology, the exact same technology. So this is basically just ultrasound from Mother Earth. And it works by taking a radar wave and putting a radar wave down into the subsurface. Every time the subsurface changes, we get a bounce back from that radar wave. And we record the time it takes for that radar wave to go down and bounce and come back up. And then we can convert that into a distance and figure out how deep we're looking below the surface. The types of changes that we're looking for are changes in the type of sediment. So whether it's sand or gravel or boulders or mud. We're also looking for changes in composition. So whether it's granite or limestone or an iron-based sand or mica or any type of earth material you could think of. We're also looking for changes in what's stored between the pore spaces of the materials. So we can have air, we can have water. If we're close to a beach, we can have salt water. In this case, we might have remnant oil that is coating some of those grains in the subsurface. So all of those different things will create a slightly different response, and we'll be able to take a look at the responses that we get and kind of understand what's gone on in the past on this site. We were out here about a week.
Because the glacier retreated south to north, so that land rebounded quicker?
Well, it's because as the glacier was moving back, this land stayed depressed. So we created a hole, and all the water flowed toward the hole. And while you were still on the other side, when the ice had just crossed the St. Lawrence River into Canada, the landscape from south of Syracuse all the way down to Seneca Lakes and just past Seneca Lakes, all was tilted to the north. So all the water actually started to run toward...
That was the watershed going to St. Lawrence.
which is my next question. The Earth bounce, are we going up right now? Are we gaining some height, or we have stabilized in the past thousands of years?
So we can look at the rheology of the Earth to understand whether or not we're still springing up. And we can look at what is happening to water levels. And all the research that has been done recently suggests that all of this rebound in this area of North America was done on the coastline about 6,000 years ago, and up here probably about 4,000 years ago, maybe 3. The date is still a little bit fuzzy, and the scientists are still trying to pin some of that down. But we have basically gotten to a point where our landscape rebound is more or less stabilized, and we are no longer coming up in this location. However, if you go up to Lansom Meadows, which I mentioned was on the far tip of Newfoundland where the Viking site is, that area is still actually rebounding as a result of unloading in the glaciers because the ice left that area much, much later. So if you walk out onto our coastlines here in New York, you'll see and you'll hear the talk about sea level rising. The global rate of sea level rise is about 3 millimeters a year. The further north and the closer you get to the area of Corner Brook, which I love Newfoundland because it's a hand state, so you can represent it with your hand. Province. Sorry, excuse me. It's a hand province. So Corner Brook is right where the arm starts. And at this point, this is the hinge. So sea level is neither rising nor falling here because the land is moving at the same rate as the ocean is rising. You get up to Lansom Meadows, and at Lansom Meadows, the land is rising faster than the sea. So the Viking site is actually higher out of the water than it should be. So you walk out and you expect the Vikings to be, and their longhouses to be basically right on the beach, which is where they used to set up. But now they're well back inland because of the rise of the land out. And that sea level change that we have from Lansom Meadows down to Corner Brook, all the way down the east coast of the United States and maritime Canada, those areas are all flooded south of Corner Brook. So any trace of a Viking longhouse that might have been built right on top of the beach has probably been erased because of sea level rise. So we might never know the answer to the question of whether or not the Vikings truly made it further south into the United States, into southern Canada, but based on their stories, we have reason to believe that they probably did make it as far as Hudson Bay, if not further.
Well, the rebound of Hudson Bay lowlands is quite interesting because shipwrecks, boat wrecks are quite removed from the shore. A friend of mine was doing some archaeology and some great pictures. Hudson Bay, the wrecks, polar bears looking for life.
Exactly. And you can see some of that in other locations, and sometimes you don't even need to have that. So there's a rumor that there were 3 schooners that were sunk right off the fork, and there's a possibility that those schooners may lie between the tree and the actual water line. So we may actually have schooners associated with this time frame that are actually not in the water, but actually underneath the landscape.
Now, the bound and rebound of planet Earth, how long is that? I wonder why has that been circulating?
So it's very well known, and there's other things that we've looked at that relate to it, that not only relate to how sea level changes and how we understand what sea level is doing, but we also understand it from looking at plate tectonics and earthquakes and volcanoes, and we can get, because we have satellites that measure the shape of the Earth on a really regular basis, one of them is TOPEX Poseidon, we actually can map out how the Earth actually changes in gravitational field. We all know there are tides, right? That the sun and the moon pull on the water and create bulges of water and allow us to have high tides and low tides across the surface of the Earth, depending on where you are on a 24-hour cycle. There is some indication that there is what's called an earth tide, which, because we have a liquid mantle that's below the hard rock crust, that liquid mantle also responds to the gravitational pull, and that there is a slight earth tide as well that's causing bulges on various different timescales in relation to gravitational pull. So, and that's something that work is really ongoing to try to understand exactly the dynamics of it and the indications of it. But when we're talking about earth tides, we're talking like millimeters and sub-millimeters of a scale. We're not talking tides at the Bay of Fundy of 40 meters.
I got a question. I'm more interested in the equipment. I want to see it work.
Okay.
But will it also locate things like where a foundation was of a building? I know you talk about compaction.
Okay, so one of the things that GPR is great at doing is it's great at finding holes that have been filled back in. So if you think about the way that the sediments are laid down on the surface of the earth, it's just like a baker making a 7-layer chocolate torte. So chocolate, frosting, all the way up. The baker gets done with that, and right before he puts that really nice layer of frosting on the outside, somebody comes into the kitchen, takes a spoon, and digs a hole in the middle of the cake. And then the baker is coming back, so he piles all that cake back in. Well, that cake that's going back in is a mixture of cake and frosting and no longer a layer. Well, the baker doesn't realize that happened, so he comes and frosts it. And then when you cut it, you have these layers of chocolate cake and frosting that come in like this, and then there's this just jumbled mess of cake and frosting that was piled back in. It's exactly what happens when we dig a hole on the earth. We take things out that were put down in layers, in nice, evenly spaced things. We pull them out, we pile them on the side, and then we turn around and we pile it back in. So anytime that we dig a hole, we can actually identify those holes by this interruption of what would be the expected stratigraphy or the expected layering of the earth. So it's great for identifying graves. So we often use it to find unmarked graves in cemeteries, because there's always somebody that's been buried outside the fence. We use it for clandestine graves. I've used it with police forces to understand cold cases. So when we think about a foundation is exactly that. We've dug a hole, and then we put something back in it. And in fact, one of the things that we're kind of comparing, or I'm comparing this site to, is when I was in Boston, I worked in Dorchester, and we worked on the Dorchester Commons site, which is where the first settlers in Boston actually started to set up their camp. And one of the first things they did was they built a palisade wall around this common area in about 1622. And what we've been able to find out using GPR is that a palisade wall is very distinct. Is they dig a narrow trench, and they line the bottom of that trench, usually with rocks. They put the palisades in, they pack the logs that create the palisades with rocks, and then they pile dirt on top of it. So we get this really characteristic narrow disturbance that often has indications that there are boulders or cobbles along the base and possibly jumbled in the center, and then there's some sort of sedimentary cover on top of that from, once the palisades are torn down, plowing and planting grass and doing other things that you would expect on Dorchester Commons. So we have an understanding of what a palisade wall might look like, and we hope that we're going to be able to identify some of those types of features as we start to do really, really detailed grids on this site in the future. When we start looking at our detailed grids, we're going to start looking at running GPR lines that are spaced about less than a foot apart, about 9 inches, so that we can really capture anything that may have happened. This system has the capacity to resolve something that's probably in the neighborhood of about 6-7 centimeters. So something that might be about this big. So 5-pound shot might be resolved by it. Chances are it will be, because it'll be metal and it'll ring like crazy when you hit it with the electromagnetic wave from the radar. It doesn't do well in picking up individual bones because most of the bones are too small for it to actually see. But once again, if we're looking for burials, we are looking for that disturbance that usually is about 1.5 meters, 2 meters deep, 1 meter wide, 2 meters long. Pretty pretty characteristic signature of what a grave looks like. So that's how we're going to use this on the site to try to understand what might have been here and how the site's laid out, and are there other things that are out this way, like gardens or stables or other outbuildings or possible cemeteries or other things like that that might be located on this point that we might be able to help find and help tell the story of what happened here over the past centuries.
Has anyone discussed with you where the British cemetery may be some blocks
Yes,
from here?
and we understand the French cemetery may be right up here.
Hill there, yeah.
And that is something that I've been working with the board about, trying to think if we might be able to do some work there to really pin down where there may or may not be burials on some of those locations.
Let's do it.
You want to run it? You want to play with the toys? All right, so Lisa's going to be our sled dog. She's going to drag the GPR around for us. And I'll walk with whoever would like to play with the electronics. What I will caution you about is this nice long cable. Just make sure that you don't step on it as it hits the steep ball.
Oh, you! So the trees are they a problem in your research?
Maybe.
Like this cluster here.
Well, first of all, one of the problems is we can't actually get there. The other thing is that the root systems will often disturb the sediments. So we'll see roots that could go down, but we can start to look at the areas around it and start to put together a map of what may or may not be there.
So does all this get like stored on a hard drive or something?
It does. This is all digital. It's all nothing but ones and zeros
And
in
how-
cyberspace.
How much data can you hold? Like gigabytes or?
Gigabytes.
Yeah.
Yeah. Okay. So this has a wheel on it, and every time this wheel turns 5 centimeters, it's going to emit a pulse. And we're going to look at those pulses as they roll up on the screen. So we're going to start a new line for you. So this is a really simple thing. All you have to do is push the big black button. Okay. It woke the screen back up. You saw how it got brighter. You just press it again because new is highlighted. The screen will go gray or white. And as soon as Lisa starts walking, you'll start to see gray lines come in from this side. And those gray lines are what we're seeing as a representation of what's below our feet. Go ahead. So in order to actually survey a site, it would take us the same amount of time as it would take to basically mow the area with an old-fashioned reel push mower.
That's what you were saying, Danielle. That's what you were saying. Lawnmower.
Just so that you keep in mind that you don't have to be quite that close, and you can be off to the side so that you don't step on it and trip. But you just have to remember that you are tethered to Lisa by a cable.
Which you have.
Which I have, to make sure that nobody steps on it.
I'm going to assume that this has GPS, so it knows exactly where it is.
It does. The
Okay.
little black box on the top of it is a differential GPS system.
Okay.
When we come out here and do the full-blown survey for real, and when we're not doing reconnaissance, we'll hook it up to something that's called a real-time kinematic GPS system, which will correct it so that we have resolution in north, south, east, west, and vertical that would fit inside a golf ball.
Awesome.
Well, we're getting some different types of lines.
Well, that's good. That's what we're looking for. So that's the whole point of when we look at this. We look for patterns, and we look for how these black and white lines relate to each other. And that will give us an indication of what we might see. Kind of like exactly what I described with the 7-layer chocolate torte. We do a grid. We'll lay out a grid and do it.
How do you lay out the lines? I was just wondering how you laid out the grid so you're walking.
So
make sure you're
we put
parallel each time you go across.
we put flags out on
Okay.
it. The other thing that we often like to do is wait till it snows and run it over the snow, and then we can see exactly where we've gone.
Yeah.
All right, Lisa?
Genius.
Okay, so now we hit stop, so press the button again. And this is our record. And we're seeing some really kind of bizarre things. So we've got this really big dip, this right here, with this response underneath it. All of this kind of really horizontal looking stuff is interference from something that's in the subsurface. So things that are in the subsurface that will cause that are things like clays that are highly electrolytic. So we know that clays can conduct electricity really well. Think of ceramics. We use ceramics for semiconductors and things like that. So wet clay will really cause problems with our system. If we look back in the record a little bit, back toward where we started, we can see we have an area where we can actually see a lot more into the subsurface. And you can see we have these lines that are much brighter and much more horizontal than this squiggly nature. This squiggly nature that we see down here is probably something that might relate to like the sub-lake glacial sediments that we talked about, that might be boulders and cobbles and till and things like that. And then this could possibly be cultural. You know, we're looking at an area where it may have an overcompacted floor. We know that from the excavations they found cobbles and planks and cobbles on top of it. So, but just running one line is not going to give us the answer. Once we actually take do all of our lines, we can make a pseudo 3D version out of it and start to relate this feature on this line to what happens on that line next to it, the line next to it, the line next to it, and we look for things that create continuous features. Because any one thing that we find on any one line, if we don't find it on the line to the left of it or the line to the right of it, means it's something that's really small and just a little bit of an anomaly. And when we're starting to look for a fort that we understand was probably 150 feet by 150 feet, we start thinking about something that is pretty good size, that we should have numerous features that are continuous over longer distances. And that's exactly how we're gonna do this as we come out here to do the survey in a more detailed fashion.
How deep is that?
So that depends on the types of sediments that we have. So like I just said right here, we're not getting very far because of the composition of the fill and possibly any type of contamination that might exist in the subsurface that's related to either the dump that was here or the oil contamination that was some of it was removed from the sediments. I've used this system in Australia on pure quartz sand dunes, which is the ideal thing, and this will go 15 meters. I have another antenna that'll go about 32 and another one that will go about 60. So we can see really deep if we have the right conditions. Now, when we run into these
send me your
areas where
pictures,
there's
video, I think
some
I'd
degree
appreciate
of contamination that gives us or something in the subsurface that gives us this kind of wiped out horizontal line record, that's when we switch over to a different system. And that's where we use electrical resistivity, because we're going to use the electrical nature of the subsurface to our benefit to be able to map it out and look at, instead of the differences in grains, we're going to look at the differences in the electrical properties of the sediments. So clay, really good conductor of electricity. Beach sand, really bad conductor of electricity. So if you were to have sand over clay or clay over sand, those would resolve really well with an electrical system. And using the two systems in conjunction with each other, we can start to answer a lot of the questions that we have. This is a geophysical system, and those are typically what we call non-unique solutions. So we can look at these lines and I can tell you a whole bunch of different stories that are all plausible based on what I see on this screen. Once we add another technique in, we start to eliminate possibilities and start to hone in on what is the more realistic situation that we have beneath our feet.
Have you taken still pictures at all?
You said you'd come back later.
Oh, okay.
So probably somewhere 9-12 inches, depending.
Well,
So
at least the equipment.
the other way as
We
well?
would absolutely do
Okay.
cross patterns, because there are things that show up better when you cross them one direction or another. So if you think about a trench, so if a trench ran from me to you, the ideal way that you'd want to find that trench is by walking this way across the trench, because you would see that sharp edge on this side, you'd see the sharp edge on that side. If we ran this way and we were right smack dab in the trench, we might not be able to exactly understand what we're seeing. Not to mention, if we're looking at a palisade trench, you could hide a palisade trench in between a 1 foot spaced line. So we want to be able to resolve things in a way that makes sense. So the palisade walls that run this way, we'd catch with lines that run this way. With the palisade lines that run this way, we'd catch with lines that run that way. And then we can start to build all this together in terms of looking at it from either a east-west pattern, a pseudo-north-south pattern, or all of it together as an overlapping grid to be able to understand what makes the most sense to be able to see the features that we're really interested in.
Center of the fort is right here.
Yep.
My shadow more than anything.
Yep. And hopefully what we'll end up doing is be able to take some of the really fantastic
you can see the wavy lines.
graphical representations that have been done for what the fort looked like and marry it with subsurface data to really map out
It's cool.
where the point actually was, where the fort was on that point, if there are other features that related to any type of habitation at some point, whether it might be gardens or stables or outbuildings or privies or anything like that, and kind of start to build a greater understanding of what the environment looked like back in that 1812 to 1749. Thank
Just
you.
roughly.
In that,
And the Abbey jumped in.
yeah, in about that 70-year time frame, because once again, you know, they did phases of building and phases of modification, so we might be able to find something that looked like, hey, this was the very first thing that they put here. It's really small, and then it kind of expanded to get to what it was, and then when it was abandoned, what happened to it, and how was that, and also what's left, because we know that they put stuff on top of this. The rail yard, the oil terminal, the dump, when they moved all that stuff around, did they actually erase the trace of the fort by digging too deep, or by using techniques that would just completely disturb the subsurface? So when you plow a field, you get almost a 2.5 foot depth of disturbance when you plow a farm field. So you can start thinking about what that might look like if they used modern building techniques when Exxon was here or when the rail yard was here, what that might have done to the fort below it. So there might only be pieces of it that are available to be able to investigate. And that's one of the beauties of this system, is we can kind of pick spots to focus our effort on and realize that there may not be anything over here because that whole area has been really disturbed, but here we have a good chance.
So what did you actually find to locate the chapel?
So we didn't find the chapel per se. What we found was the edge of an excavation that was done in 2007.
Okay.
So we found the edge of the excavation that identified the chapel, or what they thought was the chapel.
Okay.
So that stake is the northwest corner of the excavation that revealed what they thought was the chapel through the archaeological work. Yep. So we can go back over to the shade.
Run the machine back through.
We can, if somebody else would like to take a look.
Danielle?
Sure.
Okay, she wants. Okay.
Here you go. Let's get this.
That's the future. Already done this.
Okay.
You got a few.
So as soon as Lisa starts walking, we'll let you take a look at it and see what you see. Okay. Hey, Lisa, head kind of diagonally across to the, stay to the left of the little dirt pile, and kind of head to the little break in the trees. We'll go a little bit different way and we'll cross over. Yep. So you can see the cars through the trees?
No.
And stay to the left of the dirt pile.
Well, look at that. You just learned something new today.
So how long would it take to do this whole site?
So as long as it would take to mow it twice with an old push mower.
Yeah. It's not too bad.
No, and it creates an incredible amount of data that we then have to deal with.
I was going to say, who gets to analyze it all? You?
That's why I have students who work in my lab.
Okay.
But it would be a combination of different individuals working on different aspects and different parts of it
Yeah.
to try to understand what we have in the subsurface.
And you build a 3D model?
We would build a 3D block model of what we find, and then we'd be able to overlay it on any other type of data we have, like air photos and satellite images.
Yeah.
And
Cool.
related to what some of the work that had been done by some of the members of the board.
Yeah.
Okay.
A couple years ago, my wife and I went up to Newfoundland, and we went up to the Viking area up there. That was pretty cool.
So you can see that as we came across, we're in this area right in through here that looks really messy. And this area that's really messy is what we're standing on, which is where they destroyed the house. So they took the house out and they backfilled the area that it was in.
So where's the mess? It's right there?
Under your feet.
No, no,
Yeah.
right there, huh?
So the edge of the excavation for the chapel is probably this feature right here.
How do you know?
So part of it is that there's a distance scale across the top, and we know roughly how far we've walked. So we can kind of put it back, and this is the type of signature I would expect to see.